So what I'm going to go on to now is a more complicated case which has more than two groups. So if I'm doing more than two groups, I can't compare the mean of one group to the mean of another because I've got more than two. So what I do is a process called ANOVA, which stands for Analysis of Variance. So logically at this point you should be going, why is it analysis of variance? Because I want to compare means. Now imagine that I collect some data and everybody comes from the same population. So in total, on average, all of the groups and samples I collect should have about the same mean and the same standard deviation. I'm going to have some differences because of sampling. Now, if I'm mixing together data from two different populations which have different means, then I'm going to end up with a mean of the combined group, which is going to be in the middle of the means of the separate groups. And I'm going to end up with a variation which makes it wider, because basically I'm going to draw a normal distribution, one of those bell-shaped curves. Instead of it being drawn over one distribution, it's drawn over two, which are separated a bit. So it's going to be wider. So what you do for an ANOVA is you pull all the data together, calculate the mean and standard deviation, or the variance, and then do it for each of the separate groups. So if the variance changes a lot between the values you find in the individual groups and the value that you find in the pooled group when you put it all together, then there's a difference. That's what Levine's test was doing, which is a variant of the F-test, and F stands for Fisher. So we're calculating what's called the F-test statistic. Now I have a bit of a problem with the F-test because the F could stand for something else, because that's what I think of it. The problem with the F-test is that it's the first step of many, and you could quite easily get away without doing it if you just looked at your data. So let's do one. So analyze, compare means. This is an example of what's called one-way ANOVA. I'm not going to do two-way, we'll stick with one-way, that's far enough complications. So I've got one-way ANOVA. Why is it in the wrong set? Analyze. Compare means one-way ANOVA. I've only got two things. I've got three different groups of height. This is the height data that you typed in the first practical, and I've got the student heights in centimeters. So the dependent variable is the student height, and the groups, the factor is the group. Now in this case, it's nice and easy because they're called 1, 2, and 3. In the old days, SPSS would only allow you to call the groups 1, 2, and 3. So if you had it as 3 named locations or 3 ethnic groups, you would have to then recode it to a number. Now it will actually allow you to use text names for the grouping variable. So I can, once I've put the outcome variable, which is height, and the student groups, I can just go OK, and it calculates it. So here's my one-way ANOVA. It tells me that this is the amount of variation that's between the groups, this is the amount of variation that's within the groups, this is the F statistic calculated, and here's the p-value. So it's telling me that there's no significant value difference between these three groups in height. That's all great and fantastic, but imagine it had said that there was a significant difference. That's very nice, isn't it? But that's not what I want to know. I want to know, what is the specific difference? Is it 1's different to 2, or 2's different to 3, or 2's different to 1 and 3, or what? So the problem with ANOVA is once you've done ANOVA, you need to do something else, which is called post hoc analysis. So here already I found it's not significant. If it was significant, it would make more sense to do the post hoc analysis, but I'm going to show you how to do it anyway. So when you go to analyze and you go to compare means and you go to one-way ANOVA, you have these things here which are contrast, post hoc, options, and bootstrap. The only one I want you to ever think about is post hoc. So you click on post hoc, and what it will then do is the t-tests between each of the groups. So in this case, it will do 1 against 2, 1 against 3, and 2 against 3. So it will do 3 different t-tests. Now, because I've done the t-test 3 times, I have to correct for me doing it 3 times, because I'm doing multiple testing. Because the problem is your p-value tells you that you're going to get something wrong 1 in 20 times. So if I do 20 of these tests, one of them will show me a significant difference even when it's not there. So what I need to do is take into account that I'm repeating the test over and over, and so modify the p-value that I'm looking for. Now, you can do this in your brain by just going, I've got to split the 0.05 across however many tests I do. So if I've got it across 10 tests, the 0.05 becomes 0.005 on each of the tests. So in total, that will correspond to 0.05. That is called Bonferroni's correction. So when you click on post hoc analysis in SPSS, it tells you all of these different ways of correcting. So I've just told you how Bonferroni works. There is also SIDAC, Schieffer's, and lots of others, depending on equal variance and non-equal variances and whatever else. Usually, regardless of the fact that most cases they're not equal variances, so we should only pick these 3, we tend to use Bonferroni, SIDAC, or Schieffer's. So I can press continue, and now I can press OK. So instead of having just the ANOVA table, which is what I had before, this thing, I then have another table which shows me all of the comparisons. The only thing you need to look at is the sig values that go down here to see if any of them are less than 0.05. So you can see none of the ones from Schieffer are, though the difference between 1 and 2 is 0.90, which is the closest it gets to 0.05. All the other ones are pretty much the same. For Bonferroni, it's 0.89 between 1 and 2, and for SIDAC, it is 0.87 between the groups 1 and 2. So 1 and 2 have the biggest differences. All the rest of the differences are pretty pointless. Could I have told that was going to happen before I actually bothered doing all the hypothesis testing? So if I'd have done a box plot, I'd have put the student groups along the y-axis, and I'd put their height along the student groups along the x-axis and their heights along the y-axis, and gone OK, I'd have seen that 1 and 3 overlap completely, 2 and 3 overlap completely, 1 and 2 perhaps they're getting towards a bit of a difference so that they don't overlap. So this is why I don't really like the F-test, because it doesn't tell you anything other than there's a difference. So if I've got not just 3 groups, but 1,000 groups, and it says, yes, there's a difference in these 1,000 groups, I've still got a lot of work to do before I can figure out what the actual difference that matters is. So it's a bit of a rubbish technique, but you have to do it, otherwise your referees will reject your paper and say you've not done it properly. But to my mind, it's perfectly valid just to do the box plot and say, oh look, there's likely to be a difference between these ones, therefore I will do the t-test between these 2 groups. So if I did the t-test between group 1 and 2, what happens if I do that? Compare means, independent samples, heights, groups, define groups, group 1 and group 2, continue, press OK. And there is a significant difference both in the 1 and 2 sided. If I'd had chosen just to do that single hypothesis test rather than doing the 3 of them. So this is the part where you get to see that statistics is a lot about experience and perspective of how you want to do it, And there's not necessarily an absolutely correct way of doing it that every statistician would do. Different people will do it in different ways. So I've just shown you, if I looked at the box plot, decided only to do the t-test between group 1 and 2, I find a significant difference because I decided to do it that way. So when I write my paper, I can say there's a significant difference between these two groups, which I thought was going to happen because one of them was 5-year-olds and the other was 7-year-olds. If I've got a reason to do that test, if I've got a reason to focus on a specific thing, so long as I do it before I see the data and before I'm not going to get a significant test doing it another way, then I can do my statistics however I want to. But I have to make my decisions before I calculate them. I can't just keep going through and calculating things until I find something significantly different. That's data dredging and is extremely bad practice and what an awful lot of scientists do.